Hello, friends. Uh, After a long time, we are starting a new session, and in this session, we are going to discuss about overcurrent and earth fault protection relays. This will be a series of sessions, series of videos on all the theoretical aspects of overcurrent and earth fault protective relaying, and thereafter we will discuss about the implementation of these overcurrent and earth fault protective relays using numerical protection IEDs. We will discuss about the common settings and the common errors uh, during implementation of overcurrent and earth fault protection relays through all the major numerical relays like ABB, GE, Siemens, Schneider, Alstom, etc. Uh, Hopefully, we will finish these complete sessions in 6 to 7 videos, and we will try to keep each session of around 30-35 minutes only. So let us start with today's session without wasting any further time. So in this session, basically, uh, what is our outline is we will discuss about the basic concepts of overcurrent and earth fault protection. Thereafter, we will discuss about the concepts of instantaneous, time delayed, and IDMT overcurrent and earth fault protection. And then we discuss why there are so many different types of IDMT characteristics. What are the meanings of moderately inverse, extremely inverse, very inverse, or normal inverse IDMT characteristics? What else we can do using digital or numerical protective relays? Then we will discuss about the protection coordination for non-directional overcurrent and earth fault protection. And the need for directional overcurrent and earth fault protection will be discussed in detail, wherein we will discuss about the requirements, why we have a requirement of directional overcurrent and fault protection in our power system. Then the setting guidelines and application examples for overcurrent and fault protection relays shall be discussed. After that, we will discuss about the challenges in protection coordination, especially keeping in mind the coordination using overcurrent and earthquake protection only. Then we will discuss about the concepts related to the directional overcurrent earthquake protections, like the concepts of polarizing quantities, RCA, ROA, MTA, etc. Then we will discuss about the direction determination for directional overcurrent and earthquake protection in different make of numerical relays like ABB, Siemens, GE, NR, Schneider, Alstom, etc. Finally, we will also touch upon the topics of negative sequence overcurrent relay, and we will discuss briefly what is negative sequence overcurrent relay, what we have to keep in mind while implementing negative sequence based overcurrent relays in our numerical relays or digital relays. So those things will be discussed. Uh, in today's session, we will focus only the first three topics, that is the basic concepts, then the instantaneous time delayed IDMT, and the different types of IDMT characteristics. So let us see what are the basic concepts of non-directional overcurrent and fault protection. And like any other protections, this already I have discussed in our so many videos. The What are the basic purpose of any protection system? The basic purpose of any protection system is to detect abnormal conditions and isolate the faulty part of the system as quickly as possible. That means uh, there are basically three major requirements of any protection system. First is to detect the abnormal condition. Second is to isolate the faulty part, and third is to isolate the faulty parts in minimum possible time. That means its speed should be very fast. Uh, then it is again the related concept, that is discrimination, which means the protection system should isolate only the faulty section and healthy section should remain in service. Protection system should be dependable, reliable, secure. That means if the protection system is required to operate, then it must operate. At the same time, it should not operate when it is not required to operate. So now this slide is basically taken from one of the uh, PPT of SEL, and this is directly copied slide from that PPT. Uh, this slide is basically used only for to get a general idea about the overcurrent relay. So now if you see, suppose this is a generator, and this side we have a load, that is this is a radial line, and we have a protective relay at this bus. This protective relay is basically an overcurrent based relay. which measures the current flowing through this particular section. Now, suppose during a normal load conditions, we have only the load current. That load current will be the voltage measured by the relay at this location divided by the total impedance. That means the source impedance plus line impedance plus load impedance. Uh, so if you see here, this load impedance, I load is basically E divided by this, and depending upon how strong or how weak the source is and how long the line is, your load current will be determined. Finally, if we see there is any fault at this particular location, so now the total line impedance up to this location will be, suppose this is only M, a portion of line, that means total line impedance will be MZL. So the total impedance up to this point will be source impedance plus MZL. So the total fault current will be this. And if you see as compared to the above, this impedance now for the fault is very less as compared to load. So the total current, fault current will be very high. And based on this fault current magnitude, overcurrent protection is designed. So basically, an overcurrent protection basically it sees only the magnitude of current, and if that current, it is simply assuming that that current will be more than the load current, and it will simply operate depending upon the different types of methodology, like only current based or current in time or current instantaneous time delayed like this. But basically it only detects a current and it should operate after any time delay like instantaneous or any set time delay. But the problem is this protection is assuming that your fault current is more than the load current at all times. So now when the fault current and load current are in the same range, then this overcurrent relay uh, coordination becomes very difficult. For example, suppose there is a fault with a very high resistance. In that case, your fault current will be comparable to the load current, and then you cannot discriminate between the two, and the coordination will be very difficult. So we will discuss about this while discussing about the protection coordination. Now, if you see our this slide, the first two line basically what it says is that a protection system should detect abnormal condition and isolate faulty part of the system. That means now if you consider this power, portion of power system with faults at different locations. So now for a fault at location F3, only this feeder should trip and all other feeders should remain in service. Similarly, for a fault at F2, only this feeder should trip and this should not trip. For example, a fault at F1 should trip this feeder and your all the loads will be disturbed. So basically, for an overcurrent protection, the relay nearest to the fault operate first, and this is basically applicable for all. Where when we were discussing about transmission line protection, at that time also we have discussed the same thing, like the relay nearest to the fault, like zone 1 should operate faster as compared to zone 2, which should operate faster as compared to zone 3. Same is here. The relay at this location, that is suppose R3, should operate faster as compared to the relay at R2. Uh, and similarly, relay at R1 should operate after this R2. Uh, this all we will discuss in the upcoming slides that how it is done. Uh, Now, if you just see the first two requirement, that is only the faulty section is to be isolated, and that faulty section is to be isolated based on fault current, like what we have calculated here. So now you see, if we are designing a simplest form of protection, overcurrent protection, that could be a that could be a fuse. So if we have a fuse which operates for any current which is more than this, suppose this I fault is 10. So if my fuse is operating for more than 10 ampere, that means it can protect my line and my job will be done. So this is same. So this fuse is a very simple types of overcurrent protection, which operates at, with a very short time. It provides a fast fault clearance, but the problem with the fuse is first, fuse has a fixed characteristic. That fixed characteristic means uh, it doesn't matter whether the current is 10 ampere, 20 ampere, 30 amperes, it will always operate after a fixed time delay. Second thing, whenever a fuse operates, we have to replace the fuse. That means a fuse will create a single phasing. Generally, we cannot use fuse for earth fault because it has a limited sensitivity to earth fault. Now, suppose we have a portion of power system like this, and we have a fault at this position. So we have two fuse, one for this section and the second fuse for this section. Now, for this fault, what we want our fuse B to blow, not the fuse A. So, if suppose this fuse is rated for 10 ampere and this fault current we are expecting here, the fault current is 15 ampere, that means we can have this fuse here of suppose 10 ampere and this fuse here of suppose 20 ampere. That means for the 15 ampere fault only this fuse will operate, and when the fault is nearer to the source then the current will be more and this fuse will operate. Uh, but the basic problem I have already explained, it has a fixed characteristic and it need to be replaced following following of any fault clearance. So now the overcurrent protection, the basic principles. In terms of basic principles, overcurrent, we have two different principles. One is on the basis of operating speed. Overcurrent protection can be instantaneous or time delayed. Now again, time delayed, we could have definite time delay, or we could have IDMT, that is inverse definite minimum time delay relay. The discrimination of overcurrent protection is generally done by three different principles. One is current setting, that is what we have seen earlier. Uh, this fault current. So if we just set the fault current like this, for this example, suppose this fault current 10, this fault current, suppose we are assuming 20, this fault current 30, and we set the relay like this. So this relay should operate for fault current 30 ampere, this relay should operate for fault current 20 ampere, this relay should operate for fault current more than 10 ampere. Then this is called the grading, current graded scheme. We will discuss this in detail in the upcoming slides. Then the second type is time setting. Time setting could be now again instantaneous or time delayed. Generally, because we are talking about discrimination, so the time setting will be, suppose the again the same condition, even if we are assuming all these fault current to be same like 10, 10, 10, 10, 10, then we can grade this like suppose this should operate after 1 second, this relay should operate after 2 seconds, this relay should operate after 3 seconds. So in this way we can grade. This is called the time grading. Third could be the current and time setting, wherein we can coordinate both the current, that is higher the amount of current, lower should be the time of operation. Generally, overcurrent protection is the cheapest form of protection. Now, we will discuss about the first type, that is the instantaneous overcurrent protection relays. Now, this if you see 50, 50 means instantaneous overcurrent relay. When we go to the next slide, there you will see 51. 51 is uh, time delayed overcurrent protection. If you have n written with this like 50 and 51n, that means it is for earth fault. Now we have an instantaneous overcurrent based protection relay, and this is a portion of our system wherein we have one source and we have three buses with the relays at bus B and relay at bus A. Both relay are instantaneous overcurrent based relay. Now what we do during instantaneous for coordination with instantaneous overcurrent relay is that we know that these both relay, that is RB, that is this relay, and RA, that is this relay, both these relays operates instantaneously. That means if we are setting the same fault current for both relay to operate, then there is a chances of misoperation. So what we could do, if suppose this relay operates at 10 ampere, we can set this relay to operate at 20 ampere. And in that case, what happens when my fault current IF1 is supposed 12 ampere? So that means this relay A will operate instantaneously and isolate the faulty section. If the fault current IF2, now it is 22 ampere, this relay will operate. But the problem with the instantaneous relay is, suppose there is a fault at this point and your fault current IF is suppose 25 ampere. Now, for this 25 ampere is more than this, and also this 25 is more than this. That means for this particular type of fault, both relay B and relay A will operate. But ideally, we wanted only relay A to operate. So this is now a problem. So basically, what happens whenever the magnitude of IF2 and IF1 are comparable, or whenever IF1 and IF2 are equal, then we cannot coordinate using instantaneous relays because it will uh, strip all the sections. So again, this requirement that we are discussing here, that it should isolate only the faulty section, is not met. So because of these limitations of instantaneous overcurrent relay, the next type of overcurrent relay is the time delayed overcurrent relay. Now, what is the meaning of time delayed? As you see here, the important term is definite time relay. So, definite time means this relay will operate after a fixed time delay, irrespective of current. So, if we set a current of suppose IS, that is relay setting, suppose we select this current as uh, 2 ampere, or suppose we select this current as 5 ampere. So this relay will basically operate after whenever the current crosses the 2 ampere, it will operate after a definite time delay of uh, whatever the setting. Suppose 1 second, 2 second, 3 second, it will operate. So now we will see how it is done. So again, consider the same case that we were considering here. So again, we are considering the same case here. We have a portion of power system, and now, as I have already said, 51 is time delayed over current. Now consider that we have a fault here, and for this fault, whatever the fault current is, so suppose this is my fault current. So I will set my both relay. Suppose I am writing this relay as RA and this relay as RB. So I will set both RA and RAB to operate at same level of current. Suppose this also operate at 5 ampere and this also operate at 5 ampere, both in secondary, of course. Then how we can discriminate? We generally discriminate simply by the time of operation. So the first relay will operate at zero point 0.5 second, and if this relay fails to clear the fault within zero point 0.5 second, uh, then the second relay will operate. So now suppose if the fault is here, definitely for that fault the current will not flow to this relay if there is no source at that end. So the fault current will only flow through this relay, and for that fault also it will take zero point 0.9 second. So this is the major drawback of definite time relay, that we know that if a fault is closer to source, so for example if a fault is here, the impedance will be lower, that means this fault current will be higher as compared to a fault here. So for a fault current which is higher, the relay operating time is also higher. So this is the major limitation or major drawback of definite time relays. Uh, in these type of relays, the fault which is closer to the source takes longer time to clear. The second drawback is this type of relay, the time of operation is independent of fault. So now if we set our relay to operate for a current setting of more than 5, current setting of 5 ampere, and now suppose the fault current is 25 ampere, even in that 25, even for that case, this relay is going to take a minimum time of 0.5 second. So there are chances of larger damage if we implement definite time-based relay for the protection system. We will again discuss these concepts in the upcoming slides. This first session, we are just keeping it only for understanding of basic concepts. Now comes the most important part, that is the overcurrent protection using IDMT. As the name suggests, IDMT is basically inverse definite minimum time relay. Inverse definite minimum time means if you see inverse, that means higher the amount of current, lower will be the time of operation. That is inverse. And it has a minimum definite time, that is, it cannot go below this. So no matter how high the current is, it will have a minimum operating time. It cannot be zero at any time. So this type of characteristic uh, is IDMT characteristic. And now, as we already know, we have many different types of IDMT characteristics like standard inverse, uh, very inverse, then you have moderately inverse, like that. So now, uh, why we have so many different types of characteristic? Why we cannot have only a single type of characteristic, and why we are not using only single type of characteristic for all types of coordination? If you see, when you are coordinating in a distribution substation, Then you have different types of characteristic. When you are coordinating for a transformer in transmission substation, you have a different type of characteristic. When you are coordinating in a transmission in a generating stations or IVR based substation, that characteristics may be different. So why these different types of characteristics exist, and from where the different types of characteristic comes? Basically, what we already know, that whenever there is a flow of current, that flow of current has two effects. One is called thermal effect, and another is called your mechanical or mechanical or electrical effect. Uh, Mechanical forces, basically, it comes from electrical. That's why I'm saying uh, mechanical or electrical effect. So what does thermal effect means? Whenever there is a flow of current, so with this flow of current for any time, suppose this current flow for time t, then you have a rise in temperature. And now every electrical device has some insulation, we designed for some level of insulation, and that insulation has its property. So now when the temperature rises, and after some time, if it crosses the thermal limit of that particular device, then device is going to fail. So that is the one condition, thermal. Second is your mechanical damage. Suppose we have a conductor like this, parallel conductor, in any machine, in any power system. So now when a fault current comes, because of this fault current, suppose in any direction, in one conductor and the second conductor, it can be like this, it can be like this in the same direction. So for any flow of current, we know that there will be a force acting on these conductors, that is your BIL, force is BIL. So now depending upon the intensity of the magnetic field and depending upon the amount of the current, we will have uh, force acting on these conductors, and depending upon the direction of these conductors with respect to the magnetic field, these forces on the two conductors could be attractive or could be repulsive, and this may damage these conductors. So every equipment have limitations, that it can sustain a certain limit of current uh, above its normal rated current for a certain amount of time. Now, suppose we try to understand this. Suppose this is your maximum thermal limit, and this is my. I am only understanding here the simple thermal damage. So suppose this is the temperature, and this is time. So now, suppose we have a fault current like this. So a small fault current, uh, we know that after this amount of time, this is going to damage. Now, if the fault current rises, suppose the fault current rises, what happens? It will reach this thermal equilibrium after this time. Suppose this time is your T1 and this time is T2. Now, suppose the fault current is still higher. So, for this fault current, what happens? Suppose for this third conditions of fault current, suppose we have this fault current, and for this fault current, my time of thermal equilibrium is suppose T3. So now we can see that higher the magnitude of current, suppose this current is I1, this current is I2, this current is I3, and I3 is greater than I2, and I2 is greater than I1. So we can see that this equipment, whatever this equipment is, uh, if this is my current and this is my time. So when the current magnitude increases, suppose the current magnitude, so what we see is when the current magnitude increases, suppose the current magnitude is this one, then this equipment will reach its thermal damage limit after this time. Similarly, if you have this amount of current, so the time for its damage will be this much. If the current is still lower, the time will be higher. So that means higher the amount of current, lower will be the time required for this equipment to go to the thermal damage state. Now we have a damage curve of the equipment. That means now if we want to use a protective relay to protect this type of equipment, our protective relay should exactly match this damage curve. So we should have a relay which exactly match this damage curve. Suppose like this. So that's why now our equipment or our whatever this electromechanical or digital or numerical relay have, this relay should have a characteristic which should exactly match the damage curve of this equipment, and it should have a certain minimum distance at each point. That distance is basically called coordination time, that we will again discuss in our upcoming slides. So basically, what happens whenever we are protecting a certain type of equipment? So now every equipment will have its uh, damage curve, which can be different from every other equipment. Every electrical machine, every motors, every generators will have different types of damage curve as compared to the other. So now when we are protecting certain set of equipment, we have a certain type of damage curve. So we have to use a certain type of curve for our protective relay. Now suppose the damage curve is like this. So in that case, you have to use the characteristic of the overcurrent which should match this curve. If the damage curve is like this, we have to use the characteristic of the overcurrent which should match this type of curve. So depending upon these different types of damage curve, we have different types of IDMT characteristic. Now, when we were using the electromechanical relays, during those days we were having only fixed type of characteristics. Those characteristics were moderately inverse, normal inverse, very inverse, extremely inverse. uh, but it is not possible to have all the different types of damage curve covered under these four types of characteristics only. We could have one type of damage curve which doesn't fit in any of these types of overcurrent relay. So then there is a problem. That's why if you see any modern numerical relay, it gives you a flexibility wherein you can draw the custom characteristic for the overcurrent types of relay. And we will discuss about this in details while discussing about the implementation of overcurrent earth fault relays through different types of numerical relays. Uh, Since this is the first session, we will keep this session only up to this point. We will discuss about the coordination in the upcoming session. And since this is a first session, so we have kept this session only to some very basic concepts. We have not gone into the details and not gone into the depth of most of the topics. We have only discussed some very fundamental concepts of overcurrent protection. In the upcoming sessions, we will discuss about the coordinations of the overcurrent relays using uh, IDMT characteristics, using uh, different types of IDMT characteristics, how to do grading, how to calculate the time of operation, what is the meaning of TMS. So everything, these types of things that we are going to discuss in the upcoming slides. Hopefully, whatever explained in today's session are clear to all of you, and we will keep for this session only up to this point, and we will meet again shortly. Till then, thank you and goodbye.